Hello and welcome to lecture 3 of Energy in Phys 1101. And in this lecture we're going to sort of do a survey of the types of energy, and we're going to pay particular attention to spring potential energy. Before we get into discussing how to use energy to deal with springs and other things that cause position-dependent forces, let's just see why we get into such trouble if we try and use the methods we know. So here's a spring, and it's got a stiffness of 200 newtons per meter, right? The spring constant, or stiffness, is a property of the spring. Every spring has a different value of K, and this one's is 200 newtons per meter. And you can see from the units what that means. For every meter we stretch or compress this spring, it will exert a force of 200 newtons. And we attach a mass, say 100 grams, to one end, and we pull it out. It has an equilibrium length, right? A length that it is if you don't exert any force on it, of 5 centimeters. And we pull it out to a length of 10 centimeters. And then we let go of the mass, and the mass is going to accelerate in because the spring will pull on it. And let's say we want to know how fast this mass is going as the spring is 7 centimeters long. So I've drawn the free body diagram. Who cares about the normal and the weight, right? Let's say this is an air puck or something so that we don't have to worry about friction. The normal and weight are just going to cancel. All we care about is the sum of our forces in the x direction. And I have set x positive to the left because that's the direction all our leftward vectors are. And now you might ask, do I need to worry about this negative here? Remember what that negative does. It says that the spring force is in the opposite direction to the displacement, the stretch or compression of the spring. We've already taken care of that. We've already figured out the direction of Fs. So the negative is basically already buried in here. And so I shouldn't have to deal with that anymore. I can now just deal with the magnitude of Fs, right? And the magnitude of Fs is just k delta x. No vector symbols, so that's the magnitude of the displacement, the magnitude of Fs. And I advocate that you generally treat spring forces this way. You figure out the direction using reasoning with physics, and then deal with magnitudes. So I can rewrite this as just k delta x equals ma. And that delta x is the magnitude of the displacement of the end of the spring. So at time 1, I can use delta x1, which is just 5 centimeters. The spring has been stretched by 5 centimeters. And so I can solve for the acceleration at time 1. It's just k times delta x1 over m. And so that is 200 newtons per meter times our 5 centimeters. So careful. 0.05 meters all over our 100 grams, or 0.1 kilograms. And if you work out, that is actually 100 meters per second squared. It's quite a large acceleration, but this is a pretty stiff spring. And now, notice what will happen if we want to know this v. Well, the thing is, we can't use UAM because as the spring pulls in, it's less and less stretched, and this force changes, and so we'll have a non-uniform acceleration. And you might think, well, what if we can draw an F, or an F versus T graph? Well, we know it's going to start off at, work that out, it's going to be 10 newtons. But the thing is, we know F versus x is a straight line, right? That's a linear function. But x versus t isn't even going to be linear because this thing is speeding up as it goes. And so we don't know what the shape of this is. It's going to be some curvy function. And so if we wanted to use impulse, like we just learned in the last unit, well, we've got a problem, because we might like to find the area under this curve, but we don't even know the shape of this curve. So we can't do that. And so now we're well and truly stuck. What we need to know is what's called the spring potential energy. Just like we worked out the gravitational potential energy, which you can think of as energy stored in the height of an object, we need to know how to calculate the energy stored in a spring that's been stretched or compressed. Here's the thing, though. Remember that the way we worked out the gravitational potential energy was using uniformly accelerated motion. And with a spring, that's not what we get. But we know a few things. We know that it must depend on how much the spring is compressed or stretched. You know, continuing the theme of ways that you shouldn't hammer a nail, you could attach a hammer onto a spring, and if you compress it a little, well, you know, that hammer now has some capacity to do work on the nail. But if you compress the spring more, this hammer now has more capacity to do work on the nail. If you release this one, it might drive the nail fairly far. This one, not so far. But it should also depend on the stiffness of your spring. A spring like this, you could probably use to drive a nail. A spring like this, not so much. Here is an experiment that you could do to figure out the answer. You could take a known mass and put it onto a vertical spring and compress the spring under the mass and launch that mass upward and look at how high it goes. So we're talking about its maximum height when it's stationary. And so now you've set up a situation where initially you've stored a bunch of energy as spring potential energy, and at maximum height, all the energy in the system is going to be the gravitational potential energy of the mass, and you could now compress the spring by different amounts and see how high the mass goes, and you could swap the spring out for a stiffer one. And what you would find is that if you double the compression of the spring, the mass will go 4 times as high. And we know that the gravitational potential energy is proportional to the height. And so that's just telling you that doubling the spring compression quadruples the energy. And so the spring potential energy goes as the amount of compression or stretch squared. And if you swap it out for a spring that's twice as stiff, then you find that the mass will go twice as high, and so the spring potential energy is proportional to the stiffness. So the experiment I've just described could certainly be done, and it would give you what you would call an empirical determination or an experimental determination of the spring potential energy. And it turns out, if you do that carefully, you would find that the spring potential energy is a half k, right, proportional to k, times delta x squared. Now, of course, there is a way you can derive this, but it requires that more careful definition of work that I keep promising we'll eventually have. But we're going to go with this for now, and we'll see later how we can get it from the definition of work. So let's return to this example we were looking at. We can now solve it using energy. Initially, when we let go of the mass, the spring is very stretched, and so we'll have some spring potential energy. Later on, as it passes through point 2 here, the spring is less stretched, so the system is going to have less spring potential energy, and now it's moving, so that mass now has kinetic energy. And so there is our energy bar chart. I'm going to label these US1, US2, and K2. And the only thing exerting a force that's causing any acceleration is the spring force. And so this should be all that's going on. We're going to have a better way of arguing this later, but our energy should be conserved like so. And so now we can just substitute in the different expressions. US1 is a half k delta x1 squared. US2 is a half k delta x2 squared. And K2 is a half m V2 squared. And now we just want to solve that for V2. So the first thing we can do is just multiply through by 2, and all those halves are gone. And I'm now going to say you should now solve for V2. Note, what's delta x2? Be careful with delta x2. I'm going to solve, you do so as well. Hopefully you got the same sort of solution. And note that delta x2 was 2 centimeters, right? The length was 7 centimeters, the equilibrium length is 5, so it was 2 centimeters. And if you plug that all in and check your units, right? Check that out and make sure it comes out to meters per second, you get about 2 meters per second. Notice how gravitational potential energy depends on how high something is. Spring potential energy depends on how displaced the end of a spring is. So they both depend in positions in various ways. Let's very briefly talk about some other potential energies that we won't see much in this course. So electrical potential energy is something we'll look at a lot in Phys 1201. But say you take 2 positive charges and push them together. If you then release them, they push on each other if they have the same charge, and they'll fly apart. And so you can see they gain kinetic energy. That's a sign that you had given them electrical potential energy by pushing them together, and that's now being transformed into kinetic energy. And it depends on a position, because you had to push them together. Chemical potential energy is really just electrical potential energy on the molecular scale, so it's also going to depend on position. We often treat it as though it's a spring potential energy because molecular bonds behave so much like springs. And finally, nuclear potential energy is again very similar to chemical potential energy, but instead of molecules, we're now talking about nuclei. We have one more kind of energy that we need to look at, and then next lecture we'll start putting them all together. So think of some object sliding along a surface. Friction will eventually bring it to rest. Well, that means it had some kinetic energy, but eventually all that kinetic energy is gone. So where did all that energy go? Because we believe energy is conserved. Well, the kinetic energy turned into what we call thermal energy. And as Canadians, we're pretty familiar with this. When your hands are cold, you rub them together and your hands warm up. Well, this object sliding across the surface will have warmed up as it slid across the surface, and the surface will have warmed up a little bit too. And that is where the energy is going. The kinetic energy is being transformed into thermal energy, which is more or less the warmth of the objects.